Hey guys, today we're going to be discussing the second fundamental theorem of calculus. So before we do that, we're going to go ahead and practice these questions. Here we have f of t is equal to 4t minus t squared, and capital F of x is equal to the integral from 1 to x of f of t dt. So first we're going to find what is f of x, and then we're going to find the derivative of f of x. So let's try that out. So first we need to integrate this function. So f of x is going to equal to the integral of f of t dt. So we're going to input what f of t is equal to inside my derivative here, which is 4t minus t squared dt. When we integrate, we get 4t squared over 2 minus t to the third over 3. And we want to integrate that from 1 to x. Now we can simplify the 4 over 2, so this would give us 2t squared minus t over 3, t to the third over 3 from 1 to x. So now we plug in the x to apply that fundamental theorem, and we get 2x squared minus 1 over 3 x to the third minus, now when we plug in the 1 is, 2 times 1 squared is 2 minus 1 over 3. Now in order to subtract these two numbers, we got to find a common denominator. So I'm going to put this over 3 and multiply this by 3. So this gives me 2x squared minus 1 over 3 x to the third minus 6 over 3 minus 1/3, which gives us f of x, capital F of x, is equal to 2x squared minus 1 over 3 x to the third minus 5 over 3. So now we're going to find the derivative. So f prime of x is equal to 4x minus, when you multiply the 3 with the 1/3, that cancels, so x squared, and the derivative of a constant is just 0. And if we compare this to the original question, we see here that it's pretty much the same, except instead of t here, we see x. Let's try with this example. We have f of t is equal to t to the third, and capital F of x is equal to the integral from 1 to x squared of f of t dt. So we're going to plug in f of t to find f of x, and that's going to equal to the integral from 1 to x squared of t to the third dt. When we integrate t to the third, we get 1 over 4 t to the fourth. And we're going to evaluate that from 1 to x squared. So now we plug in the x squared, and we get 1 over 4 x squared to the fourth minus 1 over 4. And then 1 to the fourth is just 1. So this is f of x, which we could actually simplify this a little bit more so we can simplify these exponents. So that would be 1 over 4 x to the 8th minus 1/4. So now this is f of x. Now when we find the derivative, capital F prime of x is going to equal to 8 over 4 x to the 7th, which can be simplified to give you 2x to the 7th. Now let's see how this relates to the second fundamental theorem, because this does not look like this, which we can kind of expect to happen. We expect, that when we take the derivative of an integral, we would end up with the original answer. But this does not exactly equal to this one, unlike here where this did equal to that. So let's see what exactly is the second fundamental theorem. Now, if you have that capital F of x is equal to the integral from a to some function, which is what we were seeing here, where one of those limits of integration is not necessarily a number, but is another function, then when you find the derivative of that integral, that's going to equal to f of g of x. So you basically input whatever this is as t, and then you multiply by the derivative of that limit of integration. So these are the two examples that we did before. So if I were to use the second fundamental theorem, what we would do to find capital F prime of x, we would plug in the x everywhere we see a t. So that would be 4x minus x squared, and then we multiply that by the derivative of that limit of integration, which is 1, which just gives me that 4x minus x squared, which is why we got that answer for the first example. Now if I do the second example, we get f prime of x. We're going to take this and plug it in for t. So that would be x squared to the third, and now I multiply that with the derivative of that limit of integration, which is 2x. When I multiply this together, x squared to the third is x to the 6th times 2x. This gives me 2x to the 7th, which is exactly what we got here when we took the derivative by hand. So what the second fundamental theorem does is it basically gives us a shortcut in terms of finding the derivative of an integral if the integral has some kind of function as one of those limits of integration. So let's try that. Now here what we have is the capital F of x is equal to the integral from 1 to cosine of x of t squared dt. So we're going to go ahead and plug in cosine x as t. So f prime of x is going to equal to cosine squared of x, since this is cosine of x squared, which this is how we would write it, times the derivative of cosine, which is negative sine. And what we would get here is negative cosine squared of x times sine of x. And this is f prime of x. Now over here, we see that the limit of integration is actually in the bottom, not on the top. In the other examples, we get that the function from the limit of integration is usually at the top. So when we plug it in, we get, or rather, like if you think about this process that we did over here, I'm just going to show you really quickly. You see that when we plug in, let's say x squared, it's the function and then minus the constant. But now it's going to be the other way around. It's going to be the constant minus the function. So if your limit of integration that has the function is in the bottom, then your answer for f prime is going to be negative, because instead of having the function minus the constant, it's the constant minus the function. So we have to take into account that there would be a negative there. So f prime of x is going to equal to negative square root of 2 minus 3x squared, because remember we plug in the function as t, and then I'm going to multiply by the derivative of 3x, which is 3. So this gives me a final answer for f prime of x as negative 3 square root of 2 minus 9x squared. And all I did there was I applied the exponent to both the 3 and the x. Let's try this example. We have f of x is equal to the integral from 1 to x squared of 6 square root of t dt. So according to the second fundamental theorem, I am going to plug in the x squared as t. So this would be 6 times the square root of x squared, and then I'm going to multiply by the derivative of x squared, which is 2x. Now we simplify. We have 6. The square root of x squared is just x, and then times 2x, and that would give me 12x squared. Now, if you're ever unsure if you got the right answer, you can always go through the process of finding the integral with the x squared, getting your answer, and then taking the derivative from that. Let's look at this final one here. We have f of x is equal to the integral of x squared to 0 of e to the cosine t dt. So because now that function is in the bottom limit of integration, that means that our answer is going to be negative. So f prime of x is going to equal to negative e cosine of x squared times the derivative of x squared, which is 2x. And this would give me a final answer of negative 2x e to the cosine of x squared. And that's basically how you apply the second fundamental theorem. Now we're going to look at a couple more examples, but using graphs, and see how we can apply that second fundamental theorem when we're given a graph instead. So we're going to look at several questions here, and not just the derivative. So we have here that picture to the right is the graph of g of t. The function f of x is defined to be f of x is equal to the integral from negative 4 to 2x of g of t dt. So we want to find the value of f of 0. And f of 0 is going to equal to the integral from negative 4 to 2 times 0, because we're plugging in x is equal to 0. So from negative 4 to 0 of g of t dt. Now because we're doing the integral of g of t, that means that I have to find the area from negative 4 to 0. Now if you notice here, right, when we have to find this integral, I'm going to have to find the area. Now here we have a triangle below the x-axis, and here we have a triangle above the x-axis. So these areas will basically cancel out. So to find this integral, I only need to really find the area of this rectangle here and the quarter circle. The rectangle has an area that is a base of 2 and a height of 1. So 2 times 1 is 2. Plus, now the area of this quarter circle. So that would be 1/4 pi times the radius, which is 2, squared. Now this 2 squared is 4. This is going to cancel with the 1/4. So I get an answer of just 2 plus pi. Now let's find the value of f prime of negative 2. In order to find any derivative value for a number, you first need the general equation for f of x. So for f prime, I mean. So f prime of x is going to equal, so now I'm looking over here. This is the second fundamental theorem. We plug in the 2x for t. So that would be g of 2x. And then I multiply by the derivative of 2x, which is 2. So f prime of x is equal to 2 times g of 2x. So now to find f prime of negative 2, we plug in negative 2 and we get 2 times g of 2 times negative 2, which is negative 4. Now we have the graph of g of t. So if we're looking for g of negative 4, I just need to know the function value, which is negative 1. So this is 2 times negative 1, which is negative 2. Let's try that again. Here we have f prime of 1. We already found the function for f prime of x. So f prime of 1 is going to equal to 2 times g of 2 times 1, which is 2. Now g of 2, I look at my graph here, is 1. So we have 2 times 1, which is 2. Now this last part here, it says to find an expression for f double prime of x. So we're not actually evaluating, we're just finding the expression. We already have a derivative here, so we're finding the second derivative, we're basing it off of this one here. So this is actually the chain rule because we have that 2x inside of g. So when we're finding an expression for f double prime of x, we would multiply 2g prime of 2x times the derivative of 2x, which is 2. So that means that the expression for f double prime of x is equal to 4g prime of 2x. Now, let's try another example. Here we have the graph of f of t. And g of x is defined to be the integral from -1 to x of f of t dt. So if we want to find g of -6, we would have to plug in the -6 into x. So g of -6 is going to equal to the integral from -1 to -6 of f of t dt. Now, if you notice when we plug in the -6, that -6 is in the upper limit of integration, but is actually less than -1. So we would have to reverse this and apply that property of integrals. So g of -6 is equal to negative from -6 to -1 of f of t dt. Now we're ready to integrate from -6 to -1. Now what we have here is this triangle that's above the x-axis, and then we have this trapezoid that is below the x-axis. So we would make this area positive and this area here negative. So we have this negative on the outside, which then I'm going to open parentheses when I calculate this area, because then I'll apply the negative afterwards. So the area of this triangle is 1/2 times the base, which is 2, times the height, which is 4, minus the area of the trapezoid, which is 1/2 times the height of the trapezoid, which is 2. Base 1 is 3 units, plus base 2, which is only 2 units. And now I'm going to calculate this area. So 1/2 and 2 here, these will cancel. So we have minus 4 minus, and this 1/2 and 2 also cancel. 3 plus 2 would be 5. So we have here negative of -1, which gives me just 1. So that would be my answer. Now we're going to find g prime of -2. So first we need the equation for the derivative. So g prime of x is going to equal, and now I'm going to apply that second fundamental theorem. So I take the x and I plug it in, so it would be f of x, and then times the derivative of x, which is just 1, so f of x. So now if I want to find g prime of -2, that is going to equal to f of -2, which I can find here on my graph. F of -2 is -2, so my answer here would be -2. Now, for this last one here, we have g double prime of -4 is what we're trying to find. So first, we're going to need the derivative of g double prime of x, or rather, we need the equation for the derivative, which is g double prime of x. Now, g prime of x is f of x, so g double prime would be f prime of x. So now I plug in the -4. So g double prime of -4 is going to equal to f prime of -4. Now f prime of -4 is going to be the slope of this line, since that's where the -4 lands. So I can calculate that slope, meaning I'm picking points on either side, or just use this one to this one here. It goes down to right 1, so that slope is -2. And that would be my value for g double prime of -4. Let's do one more final example. The continuous function f is defined on the interval from -4 to 3. Let g of x equal to 1/2 of x squared plus the integral from 0 to x of f of t dt. So this here, this is f of t, since it's stated here in the function. Now, we're going to find g of -4. So I need to plug in -4 everywhere I see an x. So 1/2 times -4 squared plus the integral from 0 to -4 of f of t dt. Now, of course, my limits here of integration are backwards, so I'm going to flip that. So here we have is 1/2 of 16, which is 8. Instead of plus, I'm going to put minus because I'm going to flip those limits. So it's from -4 to 0 of f of t dt. So now I need to take that area from -4 to 0. Now what we have here, it looks like a curve, but this is a quarter circle, and this is another quarter circle. So to find this answer, we have 8 minus, now I'm going to open my parentheses so I don't forget to subtract whatever I get for that whole answer. This area here will be negative because it is below the x-axis, so that's -1/4 pi. The radius is 1, so 1 squared, plus, now here this area is positive, that's why I put plus. This is also a quarter circle, so 1/4 pi times the radius squared, which is 3, so 3 squared. Now we work this out. We still have the 8 minus, now this will be 1 squared is 1, so then pi over 4, so -pi over 4, plus, then this is 9 pi over 4. We can subtract these two because they both have the same denominator. So 8 minus, and this will be 8 pi over 4, which is equal to 2 pi. So now we can just write our final answer, which is 8 minus 2 pi. Now we need to find the value of g prime of 3. So we need the function for g prime of x. When we apply the derivative here, 2 times 1/2 is just x, plus, now according to the second fundamental theorem, we take the x and we plug it in for t, so it would be f of x, times the derivative of x, which is just 1. So now to find g prime of 3, that would be 3 plus f of 3. Now when we look here, f of 3 is -3. So this is 3 plus -3 or -3, which is equal to 0. Final question here, we want to find the value of g double prime of 2. So again, I need the derivative of g prime. So g double prime of x is going to equal to 1 plus f prime of x. Now I plug in the 2, and that would give me 1 plus f prime of 2. If I look here, 2 is right over here on this line, so I need the slope of this line. We have this coordinate here, which is 3, -3, and then this coordinate here, which is 0, 3. So my slope here is 1, 2, 3, 4, 5, 6 over 1, 2, 3, so 6 over 3, which is -2, since it's going down. So this is 1 minus 2, and we get a final answer of -1. And that's the second fundamental theorem.